So best fit, worst fit, and first fit. So already on the day we have completed this particular kind of thing here. So మీకు మిడ్ ఎగ్జామినేషన్ క్వశ్చన్ పేపర్ ఇచ్చారు కదా అత్తిపేటకి. So open that mid examination question paper. Then so I'll give you some information based on your mid examination question paper, because some example is there in mid examination. So that is why I am supposed to. Okay. So there is a specific question in mid examinations to apply this first fit to best fit, something like that. So let me give you. Open it. So they have asked that so given memory partitions, let us consider these are the partitions where exactly they have asked. So 500 kilobytes is first one. 500 kilobytes is first partition. 100 kilobytes is the second partition. 200 kilobytes is the third partition. Not partition. It is a particular process here. And 300 kilobytes is next one. And 600 kilobytes is next one here. 600 kilobytes is the next one here. For example, this is the particular thing which is available here. Now, your 500, 600, 800, 1100, and 1117, 1800 will be there as a total size of the what do you call random access memory here. So let you can consider this is 0 to 1800. So out of this particular 18, otherwise 2000, we can take a 2000. So since why I have taken 2000 in the sense, first 200 will be gets occupied by your operating system, 0 to 2000 kilobytes, for example, for our convenience. First 200 will be gets considered as what we call operating system was resided. This is 200. And the question will continue. They have given some more information. Some more partitions are there. 212 kilobytes will be there. How that can be gets occupied. And 417 kilobytes is there. How you can gets occupied this one. And 112 kilobytes are there. How this can be gets occupied. And 426 kilobytes are there. How this can be gets occupied here. Okay, these are the first 5 processes which are already existed in the ready queue. After allocation and execution is being done, then these are the next coming processes which are waiting for execution. Okay, what are the I mean, how the allocations will be gets happened for first fit? Let me write in a shorter way, FF. How the things will be happened for best fit, that is BF. And then third one is worst fit, that so WF. How this can be happen after completion of these jobs. After completion of these jobs, how they can be gets allocated. So that is what the point, the question which was asked to you in our examination. Okay, I'd like to take the particular thing here. So up to 200 operating system, 200 to first process will be. So this is first process, second process, third process, fourth, fifth, and this is sixth, seventh, eighth, and ninth processes are there here. So then how this can be gets occupied. So first process will be taken. So process one will be taken 500 kilobytes. So 500 plus 200 will be 700 kilobytes. So it is a process P1. Then followed by 100 will be taken by next process. That is 800 kilobytes. So process 2, P2 is this one. P3 will be further 200, 800 plus 200 will be 1000. So this is 1000 kilobytes, which will be taken by process P3. and then 300. So that is 1300 will be taken by 1300 will be taken by 300. That is 1000 plus 300. That is 1300 will be the last and final address of P4. Then followed by 600 kilobytes by P5. So it will be taken. So something like this here. That is 1900 kilobytes will be taken by P5. So 1, 2, 3, 4, 5 were allocated in such a way that they have been allocated in a proper way. Now, how could you? So for time being, all these processes have been completed. For example, so all these holes are available. So this hole size will be, let me write in a way, in a way such that this is 500, the hole is 500, the hole is 100, the hole is 200, the hole is 300 again, the hole is 600 here. So like this, it could be gets available here. Now consider that all the processes have been completed. So let me strike off the process 1, process 2, process 3, so that we will consider that all processes have been completed. So which was completed, which was completed, which was completed, and everything is completed. Now, few more processes have been enter into ready queue. So sixth one 212, seventh one 417, eighth one 112. So let me say ninth one 426. Now within this particular context, how the things are being happening as far as algorithms are concerned. So let me copy this one for a while. Okay, how this can be gets occupied here in the sense. First block size is 212. Now first fit will be taken into consideration. First fit. First fit does means already I have given some information to you that. So which is the best what you call to fit that particular item, what is the best possible fit thing will be there. So that is going to be taken by that particular thing. Allocate the first hole that is big enough to fit. Allocate the first hole big enough to fit. Look at this 212, and here this is the particular hole which is available for you. So therefore, while searching, so 212 is the best fit which is going to be taken. So P6 is being gets allocated here up to 212. That is 412 will be taken care by this one here. 412. So this is up to 412. It has been taken. Okay, that is P6. So P1's whole will be divided into 2. That is 412. 212. 200 plus 212 is 412. 412 700 is one more thing here. So this will be considered as internal fragmentation. This is internal fragmentation which is available for you, and this is external fragmentation which is available for you. This is external fragmentation. Okay, like this it is being available for you. Now 417. Next process is 417. I am talking about first fit algorithm. I am talking about this one. 417 can be while searching this one. So P2 is not enough. That is 100 kilobytes is not enough, and then 200 is not enough, and 300 is not enough. So 600 is available here. Yes, 426 is going to be taken. So let me consider right away from here to here. That is 1726 is the new address will be taken care by. So sorry, not 26. I'm sorry. 1717 will be the next thing that will be considered as a process P7, which is being allocated, and this is internal fragmentation for that particular hole which was created by process P5. Okay, that is created by process P5. Process P5 has taken 600, but right now it is again P7 was allocated. This particular block is divided into two partitions. So therefore, one partition is internal fragmentation, and second one is occupied by process P7. Now going forward for next eighth process 112. 112 in the sense while searching the same. So here this 200 is okay. So therefore, it is being allocated for process P. What is that? 8. Process P8. So 800 plus 112 is 912 will be the new address they're exactly taken, and this is internal fragmentation for process P3. The hole which was made by the process P3, that is internal fragmentation. Now, moving forward, process 9, it doesn't have any space. It does not have any space. So this process is being waiting list as far as the first of it is concerned. As far as the first of it is concerned, it is waiting. This is what about the allocation which is being done. Though you are having 426 kilobytes, which is available at different places as internal and external fragmentation, 426 kilobytes of process 9 cannot be allocated because compaction could not be taken when we have to operate these algorithms. So that is what the point which we have to consider. Okay, this is first of it algorithm which is being taken. So first of it is going to be taken something like this here. This color is first of it. Okay. Now, worst fit. Let me take worst fit into consideration again. Worst fit. Worst fit does means allocate the largest hole to the next coming problem. First fit in the sense allocate the first hole that is big enough. Worst fit in the sense allocate the largest hole that is fit enough. Okay, that is fit enough. While it is being searching what is the largest hole which is available that could be allocated for this particular job. Let me copy this one somewhere else. So let me copy this one. Okay, let me take some more image size. It is 10,000. Okay, now you can see, let me copy and paste. Let me copy and paste, then you could come across this one because it's very important to know. It's very important to know. Okay, this is next one. Let me copy this snapshot as well. This snapshot also very, very important for us to understand. So let me copy this one as well. Okay, here itself I'd like to copy. Now I'm talking about what is that? Worst fit. I'm talking about worst fit at this particular point of time. Okay, worst fit. How worst fit is being done here? Let me take into consideration. So let me take the another color. Blue color will be taken for worst fit here. So worst fit does means allocate the largest hole to the process which is available in ready queue as they available. Largest hole here is before going to take this one, let me copy again because best fit is here supposed to be taken again. So let me copy this one very well. Okay, so here while searching for this one, 600 is very, very largest hole which is available here. So that 212 will be gets allocated here. 212 in the sense of 1512 is the next one. So P6 is being allocated here. So this is internal fragmentation of your job. Internal. This is external fragmentation. This is external fragmentation. Okay. That is internal fragmentation for our job. Now P6 was allocated. Then P7 has been 417, which is big enough to allot this one is 500, which is available in the name of process P1. One more hole was created, that is this one. So 417 in the sense it is being allocated 617. Let me take this one. 617 is the new, that is 617 is the new one which was allocated for what is that process P7. Now 112. Out of 112, what is the big enough to be allocated? That is 300 hole. That is P4 process has done one kind of hole here. That hole is going to be allocated for process P8. So 112 in the sense 1112. 1112 will be taken. That is, this is 1112 kilobytes. So this is process P8. And of course, this is the internal fragmentation of P7. This is internal fragmentation of P7. Now, there is no space, proper space to be allocated for this particular ninth process. It is also underweighting. Here also underweighting state. So first fit and worst fit cannot be allocate the process in a proper way. Cannot allocate the process in a proper way. It is not done. Okay, it is not done in a proper way. So that is why first fit and worst fit can be somewhat somewhat creating somewhat problem while allocating the processes in the memory of contiguous allocation. So people will be select best fit. People will be select best fit. So before going to take that one, worst fit in the sense, allocate the largest hole to the process where it is being existed in ready queue. Okay. Now, let me copy the same process one more time here. So let me copy this one. This is the actual allocation which was there, available there. And let me take this particular snapshot again because it is also very important for me to explain. So let me take this one again. This is the actual allocation of the things which are being available here. Now taking so best fit. Best fit does means allocate the smallest hole that is big enough. Smallest hole that is big enough of the process. Okay, the internal fragmentation which is left over by the first best fit is very smallest. That is the meaning. Very smallest. That is the meaning. You can see 212 process P6. While it is being taken here, the smallest hole which is best fit for this particular allocation. Let me take another color again. Let me take this color. It could be somewhat easy to. So smallest space which is being allocated for big enough as long as 212 is this one. You can see this one here. This is the particular thing. P6 is being allocated, and this is the internal fragmentation which is available for that particular process. Of course, this is external fragmentation. This is external fragmentation. However, so 1000 and so 1212 will be the new address of this one. P6 was allocated. Then nearest to 417 will be taken. The 500 will be taken as the nearest one. So that is why it will be taken. So which is 617 and allocated P7. Internal fragmentation will be this one here. This is internal fragmentation. Then 112, which is allocated nearby, is the P3 hole. So this could be taken. This could be taken. 800 plus 112 is 912 will be the new one. And this is the internal fragmentation for the process P8. Now the final one, 426, which is nearest one is 600 hole is there here. This is going to be allocated as 13 plus 17, 1726, 1726. So which is a process P9. Yes, allocated properly. This is internal fragmentation for that particular hole. So in best fit, all processes have been allocated. All processes have been allocated. In this way, so best fit, worst fit, and first fit are being done. Let me repeat, first fit in the sense allocate the first hole that is big enough. Then first fit is allocate the first hole that is big enough. Worst fit in the sense allocate the largest hole that can be fit enough. Best fit in the sense allocate the smallest hole that is big enough to allocate. That is In first fit and worst fit, internal fragmentations will be very high, whereas in best fit, internal fragmentations for the holes will be very, very, very low. So that's what we need to understand. So after completion of, for example, best fit has been taken. After completion of this one, look at this particular diagram. We do have, so here hole 1, let me take some other color. Hole 1, so hole 2, hole 3, hole 4, hole 5, hole 6, hole 7, hole 8, hole 9, and hole 10. You can see these many holes. If further number of jobs are supposed to become, then things will not be worked out in a proper way for contiguous memory allocation. Further will be there, further jobs, for example, 10th job will become with let me say some 500 kilobytes and so on so forth. They could not be allocated, though the I mean whole sizes will be available as a whole. The sizes will be available for fit the job, but they are not in a continuous manner. So compaction can be gets operated, and you can make entire thing will be in a formal way. Then you can do the operation. So it could be somewhat a tedious process to perform, a biggest process to be performed here. So therefore, to avoid this kind of thing, this kind of confusion while allocating memory to the processes, several number of processes, paging was introduced. That is the cause where exactly paging was introduced. What is the basic concept of paging here? What exactly the basic concept of paging here? Paging was actually introduced. Paging was actually introduced the concept of paging was introduced to broke this particular entire physical memory. Please consider that physical memory is random access memory, logical memory in the sense CPU addressed memory. Please, I mean, have some kind of interpretation, something like that. Physical memory in the sense, so physical memory in the sense, so random access memory kind of memory, logical memory in the sense, so CPU generated memory, CPU generated addresses actually. This is memory, this is actually addresses, CPU generated addresses. Okay, that's what you need to consider. Please consider in such a way that, so paging can be always applied. So logical addresses will be divided into pages, and physical memory can be divided into frames. So these pages or frames are always fixed sized blocks, always fixed in the size of frames and so pages. If frame size will be 10 kilobyte, one frame size will be 10 kilobyte, obviously page size also be 10 kilobytes. One frame size will be 5 kilobytes, obviously page size also be 5 kilobytes. One page size will be some 20 kilobytes, obviously, so page size also be 20 kilobytes. So the block size will be fixed, no change at all, no change at all. Okay, for time being, let me consider my memory can be seen something like this. This is my memory, and operating system was resided somewhere else. Operating system was resided at the low memory. So this is operating system where exactly it's been resided 0 to 200. I'm always taking 200 only, no problem at all. And it will be, let me say some 10,000 for example, 10. Okay, let me take 2000 only. So 2000 kilobytes. And each page size will be, for example, each page size will be so 100 kilobytes. 100 kilobytes. So therefore, this frame will be taken, let me take this is 100, Okay, let me draw in such a way that I'd like to take one particular piece of thing here. This is the thing. Okay, just wait for a while, because to understand in a better way, I'd like to take the size will be always fixed. This is the fixed size. Okay. Okay, this is the fixed size. Let me take in a particular way. And this fixed size will be, I mean, this will be divided into, so this is first frame, and second frame, something like this. This is second frame, and this is a third frame, and this is a fourth frame, and so on and so forth. Okay, so all these are different frames which are available. So look at this. This is the fourth frame, and so on and so forth. Okay, like this, it is going to be arranged. Okay, like this can be gets arranged in such a way that let me drop out something because it is not fitting enough. So let me drop out something, and then I'll copy this one in a way that, okay, consider that last one also the same size, please. Okay. So let me consider this is frame 1, this is frame 2, this is frame 3, this is frame 4, and so on and so forth. The number of frames are there. And each frame size is just 100 so kilobytes. So I don't know whether 2000 will be get satisfied or not. So this is actually 100 kilobytes, 100k, and this is again 100. This is also 100, and so on and so forth. Everything is 100 only. Everything is 100 only. There is no difference in terms of page sizes here. So everything is 100 only. This is also, please consider this is also 100. So how many? So 4, 5, 6, 7, 8, 9. 900 plus 200. That is so 1100. Let me make this one as 1100. Let me make this as 1100. Okay. Now, now what exactly the paging will be gets happen. Let me explain the concept first, then followed by your actual diagram which is supported to so paging here. The concept is, if your process P1 will be required, for example, so 275 kilobytes, for example. Okay, 275 kilobytes. Now, how this could be gets occupied in physical memory as frames in this? How many frames are required here in the sense? So this process one, size of this particular process one divided by 100 will be equal to 275. Oh, 275. So divided by 100 will be equal to 2.75. Okay, this must be always a ceiling value. This must be always a ceiling value. This notation is called a seal. This notation is called a seal. This notation is called a seal. So it is a ceiling value. So 2.75 ceiling value is 3. So you required 3 frames to store this one. 3 frames to store this one. Okay. Process 1 divided by frame size. Process 1 size divided by frame size. Then you could understand how many frames are required. As far as our example is concerned, I have taken 100 bytes as 100 kilobytes as my frame size. So that is why it required. So this one here, something like this. Okay. So let me consider these are the frames here. These are the frames which are available for me here. Frame 5, frame 6, frame 7, frame 8, and frame 9. This is ninth frame. For example, process 1 is required 3 frames. It can be randomly occupied. Randomly occupied. So process one's first frame will be this one here, first frame. Process one's second frame will be this one. Process one's third frame will be process one. So third frame will be this one. Look at this. Look at this. So process one, third frame will be this one. Please write in a smaller way. Process one, first frame. So 100 bytes will be filled here. There is no internal fragmentation. 100 kilobytes will be filled here. Here also 100 kilobytes will be filled here. Still more, how much is remained? 75. till most. So this particular frame will be filled with only 75 kilobytes. Remaining 25 kilobytes will be internal fragmentation. There is no external fragmentation in pages, paging or framing. Internal fragmentation. So this will be taken 75 kilobytes. So they could not be allocated continuously. They will be allocated at random. They will be allocated at random. Frame 1 will be there at I mean first page process page 1 is available at frame 1. Page 2 is available at frame 4. Page 3 available at frame 8. Frame 8. In this way, it is being allocated. Now, this particular process, P1 is sending for execution. P1 is sending for execution. First 100 instructions are available at frame 1. Second 100 instructions are available at frame 4. Third instruction 75 instructions are available at frame 8. CPU should be generate the addresses in such a way that first 100 for first 100 it is always referred to frame 1 only. For second 100 it is always referred to frame 4 only. Third 75 always referred to frame 8 only. But CPU can be generated page addresses only, not frame addresses. Page addresses only. CPU can be generated always pages only, not frames. Then how this could be managed? How this could be managed? Managing could be done something like this. It could be save the data in page table. Let me take some other color. Page table. It could be save the data in page table. What is the contents of the page table? What is the contents of the page table? Page table contents will be seems like this. It is a particular table n by 2 kind of page table here. So this one is seems something like this. So first column is page number PNO. Second column is frame number. So frame number. First column will be page number. Second column will be frame number. Process 1 is being executed. So first page will be available at the first frame. Second page of the process 1 is available at frame number 4. Third page will be available, third page of the process will be available because CPU is always thinking that page 1, page 2, page 3 only. It shall not be thinking that page 1, page 4 and page 8. It is always thinking that page 1, page 2, page 3 only. So page 3 of process 1 has stored at frame 8. This is the way how this could be stored. This is the way how this could be stored. Then, but in page number 1, CPU wants to execute first instruction, instruction number 1. How many number of instructions are there in page number 1, frame number 1? 100, starting from 0 to 99. How this could be? So again, this address mechanism of generating address mechanism of CPU can be seen like this. Logical address generated by CPU can be seen something like this. It could be always generate two portions. First one is page number, second one is displacement. The word displacement. First one is page number and the second one is the word displacement. In other words, it is also called as, so D does means two different words are there, displacement. Otherwise, it is also called as offset address. Offset address, either of these two. Now, how this could be managed? How this could be? So, wanted to execute first instruction of page number 1 by the CPU. So, this is the way which is going to be generated. CPU can be generate page number 1, 0th instruction. Page number 1, second instruction. Page number 1, 20th instruction. Page number 1, 100th instruction. Being generated something like that. How this could be done? How this could be done? So there is a particular diagram to be understand something like this. This diagram is very important. Previous ones are not that much important. This diagram is very important. You can see while paging is done, something like this here, paging is done. So let me consider this is my memory. This is my random access memory. And here, of course, operating system will be taken some space. Okay, leave about operating system. And this is first frame, second frame, third frame. I don't want to mention anything here right now because I just make some kind of so distribute only. So these are the frames. CPU wants to execute a particular process here. CPU, this is CPU wants to execute a particular CPU wants to execute a particular process here. It should be always generates a particular logical address, something like this. The logical address will be so page number followed by displacement will be generated. How this could be, how the instruction will be gets occurred here in the sense, obviously page numbers and frame numbers are being so stored with the page table as I told you just before. So page table can be created here. This page table can be created here. Within this particular page table, so here, this is the page number. This is the, so all these things will be, let me draw here. This is the page number, PNO. This is the frame number, so FNO. Now, this page of the, so particular page of the, so logical address is being checked into page table. Logical. So this is the page number and this is the frame number. This is frame number. Then it will be creates a physical address, something like this. This is the physical address. This is the physical address. Physical address also be same as like as logical address. So it could be generated. It is the frame number, and this frame will be copied from here to here. Whatever the page associated with the frame, that is being copied to here. Okay. Then whatever the displacement you are expected to execute, CPU wants to expected to execute, this displacement is directly forwarded here. Okay. Then therefore you could get the particular address. Then you could get the particular address. Okay. And here it is. Here it is. So this is page table. Page table. And this is main memory. This is page table and that is the main memory. Understand? In this way, the pages are being allocated and it will be get the particular value.